Hi everyone, we are in video number 2. So this video is going to be looking into how to shift the graphs of f(x) when the function changes a little bit, and then how to generate new functions from old functions and what's the meaning of the composite function. So that's what this video is going to deal with. So let me share my screen. Okay, now we have the graph of the function f(x). And we're interested in seeing how to graph the following functions. When you add c to f(x), and when you add c as an input into the function, when you multiply the function by a constant c, and then when you write f of -x. Let's take an example. Now, I have the example y is equal to square root of x. And now I want to plot what's going to happen when I have root x plus or minus 2. So I'm adding one constant to the entire expression. Now, y is equal to root x is given by the black line. And I've given you a table here, which gives me the different values for all of these three functions that I'm interested in for various values of x. And now if you notice in the columns root x and root x plus 2, root x plus 2 is just adding the number 2 to every value in the root x column. So essentially, when you start plotting this out, instead of 0, 0, you're going to plot 0, 2. Instead of 1, 1, you're going to do 1, 3, and so on. So for every point x, you have the root x function, and your root x plus 2 is just going to be 2 units there. So, and that's the graph of root of x plus 2. And by a similar logic, root of x minus 2 is just going to be 2 units less for every value of x. So instead of starting at 0, I start at minus 2, and I draw out this line. And that's the root of x minus 2. Now, the rule for us to take away from here is if you add a constant or subtract a constant, you're going to move upwards or downwards by the amount of the constant. If the constant is positive, you move upwards. If the constant is negative, when you add a negative constant, which is another way of saying when you subtract a constant, you move downwards. So that's case 1. Now let's look at the case where instead of root x, we want to plot square root of x plus 2, square root of x minus 2. And on the right side here, we have a helpful table which gives us different values of the function for various values of x. Now y is equal to root x is straightforward. And we have the domain of root x as x greater than or equal to 0. So the black line is only plotted in the positive, in the first quadrant. Now look at square root of x plus 2. Now let's look at the domain of this function. Now the domain is the one where the expression within the square root is non-negative, which is x plus 2 is greater than or equal to 0. And that gives us the domain x greater than or equal to minus 2. Now, let's look at how the function takes on values for x ranging from minus 2 up to plus 4. And that's what this column gives us. Now you see when x is minus 2, this function takes on the value 0. And then it steadily increases from there. At minus 1, it's 1. When x is 0, this function takes on the value root 2 and so on. And the green line here plots the function square root of x plus 2. So let's keep that aside. Let's look at what happens to square root of x minus 2. Again, let's look at the domain for this function. I've written it down here. The domain, this function is valid or it takes on definite values of output only when x minus 2 is greater than or equal to 0. I'll write it a bit more clearly. And that is possible when x is greater than or equal to 2. So the domain for this particular function is x greater than or equal to 2. So we look at these three values for x is equal to 2, 3, and 4. And we plot out this particular function, root of x minus 2. Now, looking at these three lines, the rule for us to take away from this example is that when you have f of x plus c, okay, where x plus c is the input into the function, if c is positive, if c is greater than 0, then you shift the curve to the left by c units. which is what's happening here. When you have plus 2, we're shifting the curve to the left by 2 units. Now, on the other hand, when you have x plus c into the function, and if c is negative, which is minus 2, then you shift the curve to the right by 2 units, which is what we're doing here. That's how we end up with this line. So that's the rule when x plus c becomes a variable. Now, let's see what happens when you multiply your function by a constant. Now, you have y is equal to root x, and 2 root x is just going to be for every x, the y is now going to be twice what it was before. So, you end up plotting this line, which is above y is equal to root x. Now, if I multiply y by say 1 by 2, if y is now 1 by 2 times root x, then that is given by this green function. And you see that if you multiply by a fraction, it's going to lie below the original function. If you multiply by a constant which is greater than 1, then it's going to lie above the function. So we're stretching it vertically. So that's what happens when you multiply. Now, in the next case, we're still multiplying, but now we're multiplying by a negative number. So we want to plot root x and minus root x. And when you multiply by a negative number, the curve is going to be the same. The values are going to be the same, but they're going to be reflected about the x-axis. So instead of being in the first quadrant, where x is positive and y is positive, they're going to reflect. And they're going to be in the fourth quadrant, where x is positive and y is negative, and you end up getting this function. So this means your function is reflected about the x-axis when you multiply by a negative number. And the last one is when you want to plot f of x and f of minus x. Now let's look at this table to understand the domain and the different domains for which each of these functions have valid outputs. So square root of x is valid only when x is greater than or equal to 0, and you have these 3 numbers. Now, when you look at square root of minus x, this expression is going to be valid only when x is less than or equal to 0. When x becomes positive, then the expression within the square root is a negative number, and that's not defined with the real space. So the domain for this function is only going to be the minus 4. It's going to be x less than or equal to 0. And I've given you a few examples of where the number is running from minus 4 to 0. And I have the value of square root of minus x. So when I plot this, when I plot square root of minus x, I will only be focusing on the negative part of the x-axis. And the function root of minus x is going to look very similar to square root of x, except that it's now in the second quadrant instead of being in the first quadrant. So it's going to be reflected about the y-axis. And so you see, that's why you see the blue line curve here is root of minus x, and it's valid only in the negative space of the, in the negative half of the x-axis, x less than or equal to 0. Now, quickly summarizing all of these rules, when you add a constant, you move upwards or downwards. When you add a constant as an input, when your functional, the input of your function itself is changed by adding a constant, then you move left or right based on the sign, whether c is positive or negative. When you multiply, you're going to stretch vertically, and the magnitude will determine whether it's going to lie above or below the original line. And when you multiply original function, and when you multiply by a negative number, you stretch vertically and you reflect about the x-axis. Now, and when you have to plot y as f of minus x, it's going to be the same as f of x, but it's going to be reflected about the y-axis. So far, so good. Now, we've had y as the dependent variable and x as the independent variable. And we've always had the dependent variable so far on the y-axis. Now, what happens if you have the dependent variable on the x-axis and there's going to be, and we have to shift graphs. Now, of course, in the earlier cases, you had x on the x-axis, which is the independent variable. And when your functional form is changing or when your input is changing, essentially it's your y, which is now going to have a new function. And we're familiar with the rules to shift graphs there. Now, what happens if your dependent variable is measured on the x-axis? Then all the rules that we saw so far, we just have to flip certain rules. So upwards will now have to be interchanged with to the right, and to the right interchanged with upwards, and downwards switched to the left. So in any vertical changes will now become horizontal changes, and horizontal changes will now become vertical changes. And that's what this box essentially summarizes. So now let me show you an example, and that should help us understand this better. Now, we are given a demand and supply function, right? And we want to find the equilibrium price and quantity. And equilibrium happens when the demand meets the supply curve. So when demand is equal to supply, so you equate these two equations, and it's easy and straightforward to find what the equilibrium price is. Plug in that price value into any of the equations, either the demand or the supply function, and you will figure out, what the equilibrium quantity is. Now, we're being told that there's an increase in supply, and the supply curve has shifted from being 10 plus 2p. It has now shifted to this 16 plus 2p. And we're asked to find the new equilibrium price and quantity. And let's try doing this by sketching the demand and supply curves. Okay. Now, what we're going to do is we're going to put price on the y-axis and the quantity on the x-axis, which is customarily the way in which demand and supply functions are depicted graphically. But if you notice how we write the demand and supply functions, you see that the demand and supply is written as a function of price. So demand and supply are the dependent variables, and price is the independent variable. And now the axes are actually flipped. Demand and supply is on the x-axis. The dependent variable is on the x-axis instead of the y-axis. Correct? Let's see how the interchanged rules play out here. Now I plot out the demand curve by demand curve is given to me as 100 minus p, and use the standard way in which you will plot it in the equation. You get 100 minus p, and then supply is 10 plus 2p, and these two intersect at price 30, quantity 70. We have equilibrium. Now supply has now shifted to we're told that it's 16 plus 2p, and that is given by this new orange line. See how that when you have a tilde, it is actually 16 plus 2p, which means I've added a constant 6. When you had the dependent variable on the vertical axis, whenever you add a constant, you're going to shift above or below, upwards or downwards. But now the dependent variable is on the horizontal axis. So any vertical movement is now going to be a horizontal movement. So instead of an upward movement, you're going to go to the right. And so the curve shifts to the right, and the new curve intersects the demand curve at this particular point. And at that point, you'll see that the price is 28, the equilibrium quantity is 72. And when you have a graph paper and you plot it out, it will match at that point. And you can also find these numbers by redoing the equations, by solving them again at the point of intersection, and you'll get the answer. So this is just to say that when your demand is constant, and when there is a supply shock, when there is a supply shock which increases your supply, it's going to push your supply curve to the right. And when demand remains unchanged, more supply in the market means that there is more quantity, and the price will also be lesser. So this is whenever there's a scarcity, or something like one that you can relate to is when if you're taking ride share service like Uber. And suppose when you're trying to find a car ride and there's just no car available, and all the rides are just costing exorbitantly high prices. And then after a while, you slowly start seeing that there are more drivers hitting the roads, and then slowly your ride share prices start falling down. That's a classic case of supply rising to meet. I mean, there is excess demand there, and then supply increases to meet the demand, and then you see it falling back into equilibrium. Now that I've given you that example, I realize that it may be a wrong example here, because in the Uber case, it's excess demand bringing forth supply. Don't get confused now. In this particular graph that we're looking at, demand remains constant, it's just a supply shock. So we'll worry only about the supply curve. Apologies for confusing you there. Anyway, So that's about how to shift graphs. And then there's a quick note on how to graph quadratic equations. And I briefly mentioned this in the previous videos. So I'm going to go past this. And we have new functions from old functions here. And what I'm going to do is I'm going to do it as a different video. So I'll stop this recording. And I'll see you in video number 3.